Professor Sparks is in Pisa for a meeting in a common project that we have, and also for some days of vacation. Despite this, he kindly accepted to give this seminar today. So we really thank you, Steve, for this. Talking about Professor Sparks is somewhat obvious to most of you. However, for the few who don't know him, I want to say that he's certainly one of the figures that has most contributed to the birth and development of modern volcanology. Professor Sparks has been hugely influential in the field of volcanology and geology. Just to give you a few examples, he has published over 400 papers. He has been awarded from and elected fellow of most of the major scholar associations in these fields. He has a distinguished record of service to the volcanological and geological community, including the presidency of the Geological Society of London and the International Association of Volcanology and Earth Interiors, among many other appointments and recognitions. However, what I think we most appreciate is Professor Sparks' special mastery to carry out quantitative studies of volcanological processes using a combination of field studies, laboratory experiments, analytical studies, and theoretical modeling. Such a multidisciplinary approach has been fundamental to better understand volcanic processes, but also generously used by Professor Sparks to advise decision makers and mitigate the volcanic risk in many circumstances worldwide. I just want to remember here his leading role for more than 15 years in the scientific management and other assessment of the eruptions of the Soufriere volcano in Montserrat. We are therefore very honored and pleased to have here today Professor Steve Sparks.
Okay.
The title of his seminar is Estimating, somewhat different from what you mentioned before, is the one I reported here. Yeah. So it's analysis of magma and eruption intensity during the 2021 explosive eruption at the Soufrière of St Vincent, West India. Steve, thank you very much again.
Thanks very much. Thank you, Augusto. It's a pleasure to be here. In fact, Augusto's caught me out that I prepared today's seminar by modifying a seminar I'd given at IUGG in Berlin. And the one bit I forgot to change was the title. So it's going to be more than this, as I'll come on to discuss. I firstly just, I've put some of my collaborators, and I'd just like to give you a little bit of background. In fact, it does relate to Montserrat. In the Montserrat eruption, Soufriere Hills eruption, we worked very closely, several of the UK scientists worked very closely with the Seismic Research Centre at Trinidad at the University of the West Indies in managing the Montserrat crisis. And so when it came to the Soufrière of St Vincent starting to show volcanic unrest in the early parts of 2020 with elevated earthquakes and some ground deformation, towards the end of the year, when it was clear an eruption was going to begin, which it did on the 27th of December 2020, our colleagues from the Seismic Research Unit invited 4 UK scientists, which was myself, Willie Aspinall, Jenny Barclay, and Paul Cole from Plymouth, to join them as a sort of overseeing advisory group in interpreting some of the monitoring data that was coming out of the St Vincent. And remember, this was right in the middle of COVID. So the Seismic Research Centre had to deal with the volcanic crisis on St Vincent during COVID, which meant their ability to monitor it was greatly limited by 2 weeks isolation and so forth. So it was very difficult with them. And so they brought us in. So we didn't actually go to St Vincent, but we had sort of weekly Zoom calls with them where they showed us the data that was emerging from the eruption, and we were able to provide some sort of suggestions about how you analyze, how you interpret the data. So it's a major crisis because I'm not going to talk a lot about that today. You may have some questions about it, but several thousand people living next to the volcano were evacuated during the crisis. Nobody was killed, or even, I think one person was injured in a car accident, and that was about it. So it was a very successful management done by our colleagues in Trinidad. So that's the background. As any eruption happens in any eruption, there's a great scientific opportunities. So I'm going to talk mostly about the science that was done. And I'm going to talk about only part of that science, but there's going to be a new book published by the Geological Society of London, special publications with 20 papers on the eruption, which includes a huge range of geology, geophysics, petrology, geochemistry, etc., and crisis management papers as well, of how they dealt with the crisis, and that will be published early next year. It's already online, so you can actually download these papers from the Geological Society of London. Now I'm just going to talk about a small part of that. Okay, so where is, if you're not familiar, if you look at the little sort of inset map, you can see where St Vincent is. It's in the southern part of the Lesser Antilles Island arc with 11 active volcanoes. And you look at the hazard map that I showed you there with the zoning map at the Seismic Research Centre. You can see in red the Soufriere Hills volcano itself, and you can see some of the seismic and ground deformation stations which were used to monitor the eruption on the map. And also you can see one of the explosions. I'm going to show you some movies from space, a little bit about what happened. So the focus of this talk really is on studies of the eruption to infer magma properties, in particular viscosities and dynamic conditions of the eruption. And so that's really the main focus of the talk today. Just a little bit of background. Start with a satellite image in the lower right-hand side. The Soufriere Hills, the Soufriere volcano in St Vincent is a composite stratovolcano. It's mostly made of basaltic andesite to silicic andesite lava flows, more towards the mafic end. And these have been from dating probably going back at least 60, 70,000 years or more in age. And it's produced a large stratovolcano. And you can see that at the summit, there's about a complex of nested craters. Perhaps I can use my cursor, I hope. You can see in the center, just there where the cursor is, that black object is the 1979 lava dome sitting in a crater. If you look a little bit to, oh no, I'm not sure I can get this cursor to work. Let's see if just there is the 1812, the crater of the 1812, a little crater. You can see there's a much larger crater structure, 2 kilometers in diameter. We don't really know very well when that formed. I'll show you some stratigraphic data a little bit later about that. But you can see it's a series of nested craters. If you look at the top photograph, you can see again the crater walls of this larger structure. So it's about 2 kilometers in diameter. And it looks like this structure has been created by multiple eruptions. There's an historical record. You can see here the history of eruptions on St Vincent's goes back to 1718. But my friend and colleague Paul Cole from Plymouth University has done stratigraphy of older eruptions, and there's clear there were eruptions in the 14th, 15th century as well, quite big Plinian scale eruptions, which might have been associated with the formation of the largest 2-kilometer diameter structure. So quite a history, and I'll be referring to this history in more detail later on. The most famous eruption, of course, in the volcano's history is 1902-3, when about 4,000 people or so were killed by pyroclastic flows. It was quite a substantial explosive eruption. And of course, there's some famous names like La and Tempest Anderson associated with documenting that eruption. It took place at the same time as Montpellier in Martinique. So that gives you a little bit of an historical context, a volcano with eruptions every few decades. Now, I'm going to start with the story of the eruption, which in really just one diagram. I'll be referring to some of the details later on, but this is what happened in 2020-21. I mentioned earlier on that there was some background seismicity and some evidence of there weren't many active, there was only one GPS site on at the time before the eruption, and I think only 3 or 4 seismometers on. So there wasn't very much information, but in earlier in 2020, there was some limited seismicity above background, not dramatic, but a bit enough to worry people. And there was some evidence from GPS of a sort of wide-scale island-scale deformation. But because there was only one active GPS station, it's not terribly good. It's not terribly clear what the pre-eruption deformation was. You can see the yellow is in the sort of precursor stage, and the first thing that's happened on the 27th of December 2020 was that a lava flow started to be effused, and where you see the orange going up to the 8th of April 2021, you had essentially 3 months of lava extrusion, and then the volcano turned explosive really rather rapidly, and you've then got this pink phase, which is the explosive phase. So this is an eruption which started out with prolonged lava extrusion and then went into about 10 days of intense explosive activity. You can see a few features here. If we go to the top diagram, you can see that this is during you can see that the seismic event count, even when the lava started coming out, is very low. And you can see that as you go along, the number of seismic events increases and increases during the lava extrusion. And then, of course, it becomes quite a bit more intense during the explosive phase, as I'll show you later. That's the RSAM, but I think I'll just focus on the displacement, the radial displacement of one of the GPS stations. That by this time they'd set up several GPS stations, incidentally, there was not just one. And you can see here the feature of it going into the lava extrusion, where that orange line is, and then during the lava extrusion, there's basically very little deformation, either before or after. While I've got that site, I'm not just show you because it make the talk too long, but there is INSAR data which shows a very, very localized deformation in the neighborhood of the lava, which can't have had a source much deeper than a kilometer. So there's some INSAR data showing some deformation, but there's no deeper deformation. And that's a sort of a really interesting feature. You can see as soon as the explosive activity starts, where that red line, you can see there's a huge dip in the GPS. And so essentially this, and there's also some INSAR in this period. And so it looks like there was a massive subsidence associated with the explosive activity at about 6 kilometers depth from MOGI models. And so the deformation really starts to, deeper deformation really responds once the explosive phase gets going. And most of that is written in the first 2 or 3 days of the explosive phase. Now, I won't go through I've got a much better plot to show you, but this is the volume with time of extruded material, and I'll show you that data in detail later. But that's the story, and I think the highlight here, the interesting highlight, is really the lack of very much deep activity, either before or during the eruption leading up to the explosive phase. Really, it's a very quiet, geophysically, it's a very quiet volcano, and that's a very interesting feature. But let's go to the extrusive phase. I'd like to pay tribute to my colleague Adam Stinton from the Montserrat Volcano Observatory, who did a lot of the actual monitoring of this. You can see on the left-hand side, 31st of December 2020, you can see a little bun-like lava dome has appeared next door to the 1979 flow. So this is on the crater floor, and you can see the flow front with the green vegetation of the 1979 lava dome, and a little bun-like lava dome appears, and this is 4 days into the eruption. By the 14th of January, that lava dome has spread and has filled the moat between the 1979 lava and the older crater wall. And you can then see it spreading out essentially around the moat, or in both directions. So it's filling up this space between the 1979, and this is a picture taken on the 2nd of March. And as I say, we've got a paper analysing this in this special issue. If we look at the map on the left-hand side, this is the map. The heavy dash is the top of the crater wall, and the little dash is the bottom of the crater wall on the moat, and the orangey centre bit is the 1979 dome, and the little dot is where the new lava extruded. And here's Adam's very nice monitoring of the spreading of this lava dome in both to the north and the south in this moat. So it's some very lovely data, and he also used photogrammetry to work out approximate heights as well. So we have some fairly good volume data. And this is the result. And this looks at the volume erupted, as a function of time in days. And you can see that the thing that I think most strikes you is that it's a very steady, linear, constant extrusion throughout this 3 months. Now, you'll see that that last dot is on the 12th of March, and we didn't get any good data after that because, no, sorry, 19th of March. We didn't get any good data from that because the weather came in and you didn't get good images. But we know from other data that's been collected that in the last day or two, there was a lot of a dramatic acceleration. And in a couple of days before the explosive eruption, the lava flow started to accelerate, and it got up to 18 cubic meters per second. It's not shown on this diagram, but the uncorrected average extrusion rate, that line, is 1.8 cubic meters per second. So very, very steady extrusion of the lava. And only at the last bit, before the explosive phase, did it accelerate, just the last couple of days. I won't bore you with all the corrections that we had to make to become dense rock equivalent and modeling the shape of the flow. But when you correct the data for various things, this is for a DRE, it's about 1.2 cubic meters per second. So that's pretty well documented. Now, I'm going to start by talking about one of the studies we did. And this goes back to work that Herbert Huppert did back in 1982 on the spreading of Newtonian viscous flows, in which if you have a symmetrical spreading viscous fluid, as in these experiments with syrup, then the radius of the blob is a function of time, and it's a function of discharge rate. and there's a viscosity in time. So clearly you can use this formula for that very early phase of spreading when it was a little bun-like extrusion, and you get 2.37 times 10 to the 10 Pascal seconds for the viscosity using Herbert's formula. And this is, of course, assumes a Newtonian fluid. We did a bit better, I think, than we did there, because now we really start to worry about uncertainty. So we did an uncertainty analysis on the errors and uncertainties in the shape and the measurements of the height and area. And so we can say that the credible interval of that number is between about 6 and 1 times 10 to the 10 Pascal second. You'll see in the photographs, you see that the dome came into this moat and then spread symmetrically around. And that once it had filled that moat, it's approximately a 2D current. And so this is the equivalent formula for a 2D current, again from Herbert's paper. So you can apply that. And this time we got, for the spreading along the moat, we got a value of 1.6 times 10 to the 10, with a credible interval of 1 to 2.5 times 10 to the 10 Pascal second. So very viscous material. And this is what we got in 1979, when the lava spread on the floor of the crater. This is the previous eruption where we've applied the same theory, and we got a rather higher viscosity for that, 2 times 10 to the 11 Pascal seconds, so about an order of magnitude higher then. Now, I'm sure this won't have escaped your notice, but this model assumes a Newtonian viscous flow. There's a lot of interesting issues about how non-Newtonianness affects these results. I think I'll leave that for those who are interested in the questions, but I'll just briefly say that there's now quite a lot of doubt in the rheological community about whether there is such a thing as yield strengths in magmas. So there's some doubt. And also a chap called Neil Barnforth, you may know from, I think, Stanford, has done some very nice analysis of non-Newtonian fluids. And I think he makes a pretty convincing case that as long as the strain rate is sort of more or less constant, having a single effective viscosity is quite a reasonable assumption. And so one can interpret these viscosities as effective viscosities at a sort of essentially with a nice steady flows, approximately Newtonian, so approximations of approximation of Newtonian is quite a good, reasonable one to come. So that's that bit. Just a few points. This is the height against length, and that theory of Herbert's suggests that the height should be proportional to the square root of the length. And you can see that the data, we've got less data here, but that seems to fit quite well. And also, these are, again, using the theory and the height versus time and length versus time. This is for the 2D current. Again, these curves are sort of for the comparison with the theory rather than regressions. Okay, so I'm going to come back to viscosity at the end of towards the end of the talk, but that's the first bit of the analysis that we did on the lava flow. And the second part I'm going to talk about is an analysis of the explosive phase. And I'm going to firstly start off by showing you a little movie from a satellite image by one of our remote sensor colleagues, Ian Renfrew, that I think he got from NOAA. And the first point about this eruption, which you can see in the film, is that the explosive phase, you're going to see sort of like 10 days of explosive activities in 2 minutes. And you're going to see so to explain what you're going to see, is you're going to see a first stage which is much more continuous. And then as the eruption goes on, it becomes more and more pulse-like with discrete explosive pulses with the repose intervals becoming longer and longer with time. Now, I'll show you this in the seismic data, but I think it's great fun to see and if I can, the film almost, there is obviously Barbados. For those of you who don't know the geography, that's Barbados, there's St Vincent, and there's that's St Vincent there, that's St Lucia. So you can see this is from NASA NOAA. That's the first explosion. This is the continuous phase in the satellite image. Now you can start seeing it puffing away. Each of these is an explosion. Remember, lots of ash over Barbados. And you can see it's slow. The time intervals are gradually increasing in the explosivity. So you're seeing a little film of essentially 10 days of explosive activity. So there's a lot. So that's it. That's okay. So there's some great geophysical data. I'd like to again pay tribute to Rodrigo Carreras, who's from the seismologist at SRC at the time, who did a great job of analysing and looking at the seismic data. And we're looking at the first explosion, and probably the RSAM rather than the amplitude is the more interesting plot, because you can see the spikiness of the, you can see an initial explosive event, where the blue arrow, that's the first explosion, and there were around 32 explosions altogether. You can see then what I call this, let's see if I can, I've lost the cursor somehow, but if you look at the plot, it's disappeared. Now, don't worry.
There should be a pointer here.
Ah. I think I'm going to.
Oh. Well, if you wanted it here.
Ah, right. Thanks, Paul. Oh, yes, thank you, Paolo. Okay, so this is hopefully the people out who are listening in from outside can see this. This is this first stage. That's that pretty continuous phase. But even here, you can see it's pretty spiky. And when we analyze this in detail, it's just that it's a lot of individual explosions, which are just very close to each other. So one cloud hasn't dispersed before the next one comes in. So it looks continuous, but it's not really. And then there's a bit of a pause, and then you can see these spikes in the RSAM, and you can see the height of the spikes and the spikes and the spacing between them get longer and longer and longer, and then the very last one on the 22nd of April. So you can see that most of the explosive activity is really over the first 3 days. And you remember that ground subsidence I mentioned is also that dramatic GPS substance. Now, there's some very nice data here, just to show you some of the data. This is the stage 1, which we mentioned. If you look at the amplitude, it's a sort of spiky mess. If you look at the RSAM, you can see there are notable individual events. And if you look at the interferogram in the frequency, you'll see that there are spikes, broadband spikes of frequency, which are very well correlated with the spikes. I'll come on to talk about those a little bit more. You can see this spike here and this spike here. So this kind of data indicates that this is a sort of pulse, very pulse-like kind of activity. And you can see these broadband spectrogram bands are quite narrow, actually. Now, I can't show you this because it's some IPGP chap called Raphael Grandin, some of you may know, who's an infrasound guy, has got some great data, but not published yet. But there's a very good correlation, I should say, between these bands and the infrasound data. So, and that's quite important to the interpretation. So that's that continuous phase. Now, to make a really, and I think quite dramatic point, which will become important in interpretation, this is again from Raphael Grandin at IPGP. Kindly allow me to use this. This is a radar image of the volcano after that first 10 hours of explosive activity. You have not only removed the entire 3 months previous lava dome, you've also removed 2/3 of the 1979 lava dome in 10 hours of explosive activity. You have created something like a 700-meter wide crater during that first phase. So that's really quite dramatic. So this is a photograph that was taken on the 10th of April, just at the end of that first stage. So this crater doesn't actually need much bigger after that. And that's an important observation. So very early on, you formed a crater and likely a pretty deep conduit in the very first phase. So that's, I think, a dramatic illustration. This is when we get into the second stage. And here you see that the spikiness in the amplitude and the RSAM is quite dramatic. And you can see the individual discrete explosions. And in the spectrogram, you can see that this is matched very beautifully by spikes in the spectrogram. Now, as I mentioned, Raphael's got some very nice infrasound data, and we're fairly confident from looking at the comparison, the seismic and the infrasound, that these spikes here are the actual explosive discharge. Whereas you can see there's a lot of noise afterwards, but that's not associated either with much going on here, or indeed the infrasound changes. So we think that these spikes here represent the duration of actual explosive discharge. All the stuff that's going on in between them afterwards is basically bits of stuff falling down the crater and rumbling around in the volcano, but it's not the actual explosive discharge. So from this data, we use these spikes to work out the duration of each explosion. So that's, and if I just go on, this is just to look at one of them in a little bit more detail. And this is our interpretation. You can see very abrupt onset, and then a fairly symmetrical spike, and then a lot of more complex wobbling around, what we call post-explosion noise, the system settling down. But you can see in the spectral analysis that coincides with this RSAM spike. So we can use the shape of this to calculate the duration of the explosion. So for each explosion, we've done that. And so this gives you a bit of that analysis. Here's one of these spikes, and this is this isn't a real fit, it's just me playing around with it, just to show you how we did it. You sort of fit this shape to and work out the duration. And of course, it's a little bit, there's some uncertainties that we think are between 15 and 30 seconds. And so the mean for the 40 explosions of duration comes out at 13.2 meters, minutes, and the standard deviation is 5.9. The longest explosion lasted 24 minutes and the shortest 2.7 minutes. So we've got, for every explosion, we've got an estimate of duration with some uncertainty. Now, the other thing that we've done, and again, that's what my colleague Ian Renfrew, who's a meteorologist at the University of East Anglia, helped us with this, was we have some very good satellite data of the cloud top. And this is some of the data, and this color-coded for plume height. Not going into enormous details, but basically most of the plumes got to between 12 and 16 kilometers. In fact, most of them are between about 14 and 16 kilometers high. And of course, we can relate that plume height to discharge rate. And here's the flow rate. So we've got a magma discharge rate. We've got the usual formula of the relationship between discharge and height. And this time we've used an uncertainty analysis for the values of these coefficients drawn from the global data, like Maston et al. So we've got uncertainties as well. And we use sort of Monte Carlo stochastic models to calculate discharge rates plus uncertainties for every eruption. And because we have a duration of every eruption, we can get a volume plus with uncertainty for every eruption. And I'm not going to go into this in any detail, but we relate the Q to the peak. We think we're getting peak heights, but of course this is the height of the peak. You can see from the seismic data it goes up. The discharge rate in reality must be going up to a peak and then going down. And so we do use a sort of rough and ready coefficient to correct for that. The fact that the peak discharge might be getting us the cloud height, but that actually over that duration, there's some sort of variation. So we include that as well. So essentially from this data, we're going to get volumes, durations, and discharge rate. I've touched something, obviously. Right. Okay. So we use this uncertainty analysis we use a piece of software called Uninet. I'm not sure how many people are aware of Uninet. It was produced by somebody called Dan Abibi at the University of Melbourne, but I think originally at Delft, but he's now in Melbourne. You can get it there. It's a stochastic analysis software. So it samples all the independent uncertainties of all the parameters and therefore gets us overall uncertainties in volume, duration, and discharge rate. And so it's this software that Willie Aston has become a sort of pilot. He's the pilot. He's done a lot of this analysis for us. So we've looked at that, and these tables are horrible. So really this is to show you that we've done this analysis of cloud height, tropopause height, and duration for all these eruptions. And this just on the bottom is the one that this is just the ninth explosion. Gives you the onset time, the duration, the surface brightness of the cloud, the tropospheric height, which is the one we use, and the stratospheric height. And so this is basically our data set, and that's that very explosive initial stage. You can see the main thing, I think, probably just to draw your attention to, this volcano seems to, when it explodes, produces really rather similar heights. They don't vary an awful lot from this analysis. And so this is the results of that analysis. This is eruption intensity for each explosion. You can see the first stage. You can see a quiet pace. So this is in cubic meters per second. This is elapsed hours. And we divided the eruption into 3 stages. There's the first stage, there's a lull. There's a stage where there's fairly regular discharge rate, and then there's one with a declining discharge rate, and these are the uncertainties. This is the magma discharge rate, and this is different because in between each explosion there's a long repose period. So we take the total erupted in each explosion and we divide that by the previous repose time. We get a magma discharge rate. It must be the rate of supply of magma into the conduit. So we're getting a different number here because we're looking at the time averaged discharge rate. So this is, of course, a significantly lower number, but you can see that we're getting magma discharge rates of a few hundred cubic meters per second. You can see the first stage, the second stage, and then a third stage where things, the magma discharge rate declines and goes off. So we've got a, it's a,
To be sure, the decline is mainly due to the fact that the
repose period is
the repose
increasing.
period.
Exactly, yes, yeah, exactly, yeah. Yes, that's right. So it's the heights are actually getting to similar heights in each explosion. So the intensity during the explosion is sort of fairly similar throughout, but the repose period is going bigger and bigger. And that's the inverse of the repose period. So again, this really just reflects the declining repose period going from with time. So that's basically the data that shows you what you saw on the film. And this is the volume. And so the volume, we can count up all the volumes of the individual explosions and do an accumulated volume with time. We can get uncertainties. There's a little bit of a trick, not a trick, but a difference in what you get from the stochastic analysis depending on how you treat the uncertainties in the coefficients which relate height to discharge rate. You can decide to keep K and N constant for all explosions, or you can decide that we'll randomly vary K and N for each explosion. And that gives you the different boundaries. We think that it's probably, there's more scientifically dependent to make them independent for each explosion, but there's a discussion to be had about that. So anyway, here's the volume. You can see that we end up with 38.5 million cubic meters in the explosive phase. I should have mentioned that the lava produces about 15. So this is about twice as much as the lava, as all the lava that came out in 3 months. And there's the credible interval from the stochastic analysis. And we've got mean erupted volumes per explosions between 0.1 and 2.46 times 10 to the 6, and an average of 1. Now, this is a table where we have 3 independent ways of estimating the volume erupted during the explosive phase. Our explosion analysis gets us 38.5 with this credible interval, quite large. Paul Cole, and I've been involved in this, analysed the tephra fall deposits. So we have a volume from the tephra fall, independent volume of the tephra fall. And just for those who know about the expert elicitation method, we used expert elicitation for several scientists to draw independent ice pack maps. And because the ash was blown out to sea, there's quite a lot of uncertainty. It landed on Barbados, so we've got some data there. And we've got a lot of data on the island, but not much in between. And that analysis gives us 31.6, and that's the credible interval. So we get a pretty similar result, and the 2 methods are about the same. The ground deformation people, I mentioned the collapse in the first three days of the explosive activity. They've estimated the volume change in the source during that explosive phase, and they get about 50 million cubic meters from their Moby model, but they didn't do any uncertainty analysis. We suspect this could be quite large, but we don't know. But it's not too different. So we have 3 independent methods of calculating uncertainties. And that's just to highlight that uncertainty analysis. I think that's going into too much detail. I'm going to now finish with a little bit more on the viscosity of the magma during the explosive phases. We asked Herbert to analyze the following problem, that if each explosion empties the conduit down to some depth and then refills it to recharge for the next explosion, how long would it take and what would the volume constraints be on that refilling process, and we did both cylindrical and diverging conduits. And I'm really going to, it's in a supplement to our paper, or the mathematical analysis, so I'm just going to give you the results. That if we know the time to refill, which we do, which the repose periods, we know that length, which we also approximately know from the seismic data. Rodrigo's calculated a source depth for of something like 2 kilometers. We don't know that very accurately, but we know it's it's around 2 kilometers from his analysis for seismicity. If we know the pressure, initial driving pressure when the conduit's empty, and the radius of the conduit, and we also have a relationship between length and radius to get volume. So length and radius can be combined to give us volume, depending on the geometry. So we have this figure too, because we've worked out the volume. So we basically know, to various degrees of approximation, the duration of filling, the pressure I'll come on to in a moment, the volume that filled the crater, and the length, and the radius drops out, fortunately, so we don't have to, we can just use the length, and that gives us a viscosity. And so we can say, we've just used in the paper, we can obviously do something a lot more with this, but the paper we just used the average refill time of 2.2 hours, average refill volume of 1.6. The real fill depth we don't know very well, and it's the major source of uncertainty, so we use between 300 and 1500. We don't need the conduit radius. And we basically worked out the driving pressure for the pressure head of a tube full of liquid, which then drops to 2 kilometers, and what would be the pressure, sort of, if you like, the magmastatic pressure drop. And so we use that to constrain a driving pressure of around 50 or 60 megapascals. Anyway, when we feed that, we get a whole range using again stochastic software. We get analyses of 1.2 times 10 to the 7 to 2.3 times 10 to the 9 pascals seconds. The main point about that, it's a very wide, uncertain number, but it's 3 to 4 orders of magnitude lower than the lava viscosity. That's their main point. So it's much, much lower. And so we believe that this is the viscosity of the magma infilling the conduit, which will be partly degassed and partly crystallized. So it's a very simple analysis. And the final thing we did, and again, I'm not going to go into details. We've got a lot of very detail from our colleagues, Gregor Weber and Holly Frey in the USA, a lot of detailed petrology. We can develop models. We know the temperature quite well. We know the phenocryst content quite well. We know the amount of microlights in the lava and the microlights in the scoria, and these are just indicative numbers. We can get from melt inclusions and other pressure depths the amount of water in the magma in the upper part of the conduit and the amount of water in the deeper source region. So we have a petrological model. I haven't got time to go through that in detail, but the petrological model gives us these viscosities which overlap with our dynamic model, but tend to be a little bit lower. So essentially what we think is that these are giving us the viscosity of the magma in the upper parts of the conduit, which are controlling the refilling rate. And then this is the magma reservoir, where the viscosity drops to 10 to the 4, an estimated 10 to the 4 pascal seconds. So you can see we've got from the source to the surface, we've gone over something like 6 or 7 orders of magnitude of viscosity in that journey from the source to the surface. Okay, just to finish off, I just wanted to go back to the history because there's a couple we've been trying to think what all this means. And I think one of the points that I'd like to make is that the history of a volcano affects what it does next. And what it does next can be profoundly different from what it did before, because the system has been profoundly changed by each eruption. So we go back to 1812. This is a picture by William Turner in 1812. Lots of fire fountaining. We don't know much about this eruption. And then we go over to 1902 for the typical volcanologist's headgear, protective headgear. I think this is the famous Tempest Anderson. This is the 1902 eruption, which was only an explosive eruption, no lava, just an explosive eruption, and quite a big one, probably about 0.7 cubic kilometers. Fast forward to 1971, there was a lake in the crater, and a lava dome formed in the crater in the lake. Virtually no seismic activity at all, or known ground deformation. This stuff just appeared at the surface. The seismic research unit had, I think, 24 hours to respond. That's the first sign that something was happening, and the lava already almost started. Go fast forward to 1979. This one formed a lava, started with explosive activity, first 10 days, and then went into a lava eruption. And that is the 1979 lava, which occurred after the explosive activity. So we've had last four eruptions have had four totally different scenarios. So that's very interesting. Why we're having, otherwise the magma's the same, it's all the same basaltic andesite. Now, been thinking about this, and it starts to get more speculative, but I want to draw your attention to this because this is our working model, and we've been having some quite interesting and passionate debates amongst the different scientists working on this. We favour a model where the lava extruded at the beginning of this eruption was lava left behind in a deep, shallow conduit from 1979 and 1971. And so we envisage a plug of lava from the previous eruption occupying an explosive conduit which had formed earlier and is just being simply pushed out. And that's why we get a very high viscosity and a very constant rate. And so this is the idea that you can store in deep, wide conduits significant amount of still mobile magma for maybe decades. And that affects what happens next. Now, there are other colleagues, to be fair, who think that this is magma that's come up from deep, and on its way, it's degassed. And because the flow rate is slow, it's been able to degas a lot, and therefore that's why it extrudes, has this very high viscosity. So I won't take you through all those arguments, but it's that's the sort of current debate. And then once the new magma, here's the new magma coming in December 2020, it's got this viscous plug, which it simply pushes out of the way. And then at the very late minute, this is consistent with this very dramatic last 2 days extrusion, the fresh volatile rich magma gets to the surface and it explodes, the explosive activity starts. And this shows you the sort of events we imagine in 1903. There was an explosive eruption and maybe there was a plug. And then this plug was pushed out in 1971. This plug was exploded in 1979 and followed by some perhaps deeper new magma that formed a dome. And then there was still remnant magma here, and this was pushed out in 2020. So that's the sort of thinking preliminary thinking we're having about interpreting the idea of remnant magma. And you may remember that big crater that formed after 10 hours, 700 meters wide at the surface, going down to 2 kilometers. It's easily enough to put quite a large volume of magma, which would remain hot for a few decades underground, ready to be extruded next time. So that's the idea. And I want to just show you the satellite image from Raphael on the 2nd of May. So this is after the eruption. That's that crater that I showed you. But you can see that the crater itself has been infilled by tuff rings in the middle. So that's the dying stages of the explosive activity. That conduit's being refilled by pyroclastic debris and material inside the crater. So we can imagine these craters filled by both residual degassed magma and pyroclastic material. And that's, so I'm going to finish there, just to keep, try and keep the time, and
Thank you, Steve, very much for this very fascinating story of these interesting eruptions. I see that there are many colleagues connected. I think we have more than 75 people. And I'm asking if there is any question or comments on Steve's question, on Steve's presentation.
I have no question.
Yeah, we have one here from Mattia.
Maybe I missed these things and you told, but in between the different explosive events, was there an effusive activity, or it was just
no fused activity? Oh, I'm sorry. Do you mean the historic events?
No. I mean in these last eruptions.
No, in that 10 days it was just explosive.
Just explosive.
No extrusion at all.
Okay.
There was only 2 hours or so in between. Yeah.
Paolo?
Yeah, I have a couple of questions. First one is related to the scheme that you showed at the end. Mm-hmm. My question is, do you think that the highly viscous magma, which was erupted and formed the dome in 2029, was staying in the conduit as a fluid, although highly viscous melt? Or is it also possible, maybe petrologists might say something about that. Do you think it's also possible that that magma was reheated and remobilized?
I think the former, although I couldn't discount the latter. The petrology is pretty interesting. The lava dome has a lot of oxidation of the titanomagmatites and olivines, the few olivines that are in it. It shows a lot of sort of corrosive features, which could be done by gases. There was one observation that I neglected to mention, which is quite important. There was essentially no SO2 at all during the extrusion of the lava. There was no evidence of any fresh magmatic gases. They couldn't detect it on the DOAS they were surveying every day. The SO2 only started 2 or 3 days. Detectable SO2 only came out 2 or 3 days before they started the explosive activity, and then it got to quite high levels, suggesting that fresh magma was on the way. So it's something I'd neglected, but I think it's one of the bits of evidence that supports this being degassed magma. As far as your question, Paolo, I think the point is that the conduit at depth only has to be around 100 meters wide to prevent the interior crystallizing very much in between 1979 and the present. So as long as it's something like 100 meters wide, then you should be able to store magma with very little temperature drop. And since we've got something 700 meters.
That's 15 million cubic
meters, yes, something like that.
So with 100 meters, how deep would it be?
I can't do it off the top of my head, but it's it's pretty long. Yeah.
124, no.
Yes, yeah.
100.
Yes, so I think you can get the volumes and they retain the heat. One of the things it does for St Vincent is that this idea that you might have mobile magma going from the source right to the surface in the dormant periods helps us explain why there's so little deformation. We don't have to deform the country rock that much. Why there's so little seismicity as precursors to the eruptions. Again, I mentioned 71, but I think it's a characteristic of the volcano that very limited pre-eruption size unrest, essential, very low level.
Yeah.
I had another one, but maybe I wait.
Maybe go ahead.
Okay. Now, this one's related to the low frequency seismicity that you showed.
Mm-hmm.
And I saw that there is a lot of low frequency seismicity, close to 10 to the minus 2, I guess. 10 to the minus 2 is the lower limit of the broadband. But there is a lot there concentrated, and there is a gap in the middle. So apparently, there is nothing at around 10 to the, between 10 to the minus 10, something like that. Sorry, 10 to the minus 1 frequency, and there is a lot around 10 to the minus 2.
Yes. Yeah.
So I'm wondering whether you have an explanation for that, or if there is someone looking at that low frequency.
I think I'm not sure. As you know, you can get a mixture of, it's sort of volcanic tremor, and there's still not entirely clear to me how the volcanic tremor forms in these eruptions. I mean, I think people talk about resonance of cracks, and I'm not sure I can easily answer why. But I think you're right, there is a sort of gap there, isn't there?
The gap is interesting.
Yes, that's right. Yeah, so I'm afraid I'll have to defer to, maybe there's a seismologist in the room who can help us, but I'm not sure I can answer that easily.
Oh, wait, we can talk about that.
Yes.
Massimo, Pompilio?
Two questions. One is about the composition. You mentioned that this can be what is remaining of the past eruption. The last, which is the difference in composition between the last eruption and the new one, and the previous one?
No,
I mean, not only, you say that in general,
yeah.
it's a basaltic design, but I mean, crystal content is changing something, or?
Yes, there are some really interesting differences, very subtle. It's all, but including 1902, it's all broadly bulk rock chemistry, the same stuff. In terms of phenocrysts, it's the same mineral assemblages, but there are subtle modal differences, and in particular, some of the microlites are distinctly different. And so, for example, the 1979 lava contains a lot of more orthoproxene microphenocrysts than clinoproxene, whereas the new lava has a different ratio. But then the difficulty is that that lava wasn't very well, is this based on just one or two samples? People have been going around museums and universities to try and find bits of rock that somebody had analysed in 1980, and they can't find them. So there's quite a question of, the new lava, of course, has got lots of samples and lots of analyses, but the older ones don't have enough samples to be really confident you've got representative samples. But there are differences. The existing 1979 ones have much more orthoproxene ground mass, which you can sort of interpret as a lower pressure crystallization, or you can. So there are differences, but they're not so easy to interpret.
The second question is about the volume. You showed that the volume of the data, the volume that comes from the estimates about 50 million.
Yeah.
But from the formation, you have 50 million. So this difference, you can assume that is the part of the matter which remain now inside the system.
I think the uncertainty in the deformation volume estimate is huge. And they just didn't, the old people who did the work just gave it as a rough and ready Mogi model. And they assumed, I don't know, a sphere, and they could have done different shapes and things, and compressibility. So I think the uncertainties are very large. So I would count 50 as equivalent to 30, about the same, yes, or not demonstrably different, shall we say?
Yeah. Other comments or questions, Matteo? Okay.
I was curious to see that the mass eruption rate for this kind of volcano was constant for a long period. But why do you think it's like that? Why do you think that there is some particular shape? Or why this volcano in this period has this typical mass eruption rate?
To the very steady one for the lava flow, do you mean?
No, for the explosions. That you showed that the explosions at the same height.
Yeah. I don't know. I suppose I'm not sure we've thought about it, but I mean, just thinking about it, if the conduit's roughly the same diameter, you're filling it to the same height, then the sort of volume available for an explosion is sort of the same. The flow conditions are sort of the same. So when it reaches the fragmentation threshold, then you'll be flowing through the same. Remember, on the day, in the first 10 hours, we formed the crater at the surface, and it didn't change after that. So the conduit is sort of fixed. Yes. So the flow rate would be sort of fixed in the explosive phase.
This is impressive because the mass eruption rate.
I had the same question. But this also means that during this explosion, we have a shock flow condition in the conduit. Do we reach a kind of steady state? Because it's really impressive that they almost have the same.
They only start to drop off right at the end. It is. And I mean, we haven't really attempted to model any of that. But I think that the observation that the crater itself and conduit is fixed very early in the eruption, I think it fits with the idea of one of the interesting things I haven't got time to mention was that Paul Cole and Jenny Barclay done a wonderful job on the tephra. And the very first explosion is absolutely full of lithic fragments. So basically, it could even be largely formed at that very first explosion, because the tephra deposits are full of fragments, probably of 1979 and the earlier lava. So it does get, and the thing that you asked about overpressure, I mean, it fits with the idea of an early stage in eruption of overpressure, and then a period of pressure adjusted, where the flow adjusts to the surface pressure. And then a period of under pressure where the flow rate starts to decline and the conduit starts to fill with debris, which you saw in the last radar image was in May, is this little tuff cone. There's now a little tuff cone in the middle of the crater. So I think it sort of broadly fits with that, that sort of evolution.
We have a question from remote. Giuseppe Puglisi is asking, Giuseppe, do you want to express it? Thanks.
No, okay, thanks. First, thanks very much, for this very interesting presentation and the story of the eruption. Okay, I already write my comment, my question. Essentially, I'm wondering whether are you able to estimate how long it could be molten the magma before erupting, and in case we have no clear evidence of this or the intrusion of the 50 million cubic meter of magma, if we have evidence of the role of the compressibility, the role of the mesh in the compressibility of the magma reservoir. So I hope that is clear, my question. I cannot hear.
Forse abbiamo perso il contatto.
I have no return.
Peppe, hanno scritto che riprendo, hanno perso.
Okay. Okay, go ahead, Giuseppe. Can you hear us?
Can you hear us?
Yeah, perfectly.
Yes.
Okay.
You heard my question?
No, I didn't. I'm afraid we cut off.
Okay, sorry, but however, you can read my essential question in the note. But okay, just to extend. Hello. Yeah. Okay. Just to complete my question, I'm wondering whether you have some evidence about the possibility to accommodate the magma before the eruption in the magma in the reservoir, and if in case okay, have evidence also of the role of the mesh in the compressibility of the magma reservoir.
Giuseppe?
Yes.
Yes. So it should be in the chat.
Ok, continua pure Giuseppe. Scusateci per questi problemi tecnici.
Comunque,
pure, ti abbiamo sentito finora, ti abbiamo sentito. Concludi pure.
Okay, no, I finished. My question is that.
Did you get the question? Did you get the question?
The question is in the chat. So you can
Okay, the question is there evidence of accumulation of 50 million cubic meter of magma in the years before the eruptions from ground deformation? In other words, how long the magma could remain molten to be erupted?
Right, I
get it.
Yes, I did. Yes, unfortunately, we can't answer that question very well, because I mentioned that there was only one GPS station on the island, and this is about 9 kilometers from the volcano. And this GPS station intriguingly shows a deformation, a horizontal radial deformation, which is, if you interpret it as a Mogi source, it's got to be quite deep because the station is 9 kilometers. And the best that the deformation people can do is to give a depth of about 15 kilometers. So before the eruption, the rather fragmentary evidence suggests a depth of 15 kilometers for a swelling of the source, but we don't have very good data. On the other hand, the petrologists are able to do more, and the phenocryst assemblage that's been done by Gregor Weber and Holly Frey and John Blundy, they've done a pretty good job of looking at the phase equilibria and melt inclusions and all that, and they come up with a depth in the phenocryst assemblage of about 15 kilometers. So it's consistent with rather fragmentary GPS data. So there's no sign of any swelling at 6 kilometers before the eruption. But whether that's because there wasn't enough GPS stations, it's unclear. But certainly the swelling, it looks like the magma is coming from a deeper source in the middle crust, about 15 kilometers deep. So, yeah, so we can't really answer your question completely, but that's what we know at the moment.
Yeah. Did you get it, Giuseppe?
Okay, thanks.
Thank you. Any other question or comments from here or from colleagues connected? No, it doesn't seem. So I think we should thank again Professor Steve Sparks for this very fascinating talk and interesting talk. So thanks again for being here and for giving this seminar today to IGV. Grazie a tutti, poi vi invieremo il link per poter vedere il seminario che abbiamo registrato per coloro che non potevano essere qui oggi. Grazie ancora.
Grazie mille.
Ancora a tutti. Grazie a voi per essere intervenuti. Ciao.
Ciao.
Ciao a tutti.
There is